All right. So glad to say everyone's all right. So we'll go straight into it. So for the final exam, the way he structured it last semester, it was mostly written. So very short response, very paragraph up to paragraph wise. So we had to write a lot. And he gave us 12 questions to compensate for the fact that it was online. So these are some of the questions. Number one, say the design performance of tissue adhesives and pros and cons. So obviously the tissue adhesive needs to meet following criteria. It needs to be wet and bonded tissues. It needs to have sufficient bonding strength. They need, when they polymerize, they can't produce excessive heat or toxicity in a way that can damage the tissues. It needs to be easily applied, sterilizable through conventional methods, and manufactured through conventional methods as well. So when you talk about the particular source of adhesion, it actually comes from these groups, these functional groups, the carboxylic acid, the hydroxyl, and amine groups in the body. And the common one used is called alkyl alpha cyanoacrylate, and just branches off from that. Variations of that alpha cyanoacrylate include the ones that are publicly sold today, like epoxy and crazy glue. So for number two, loosening of hard tissue implants, and how would you mitigate that loosening? So it depends on what the material involved. If it's ceramic, then one thing you can do is obviously include porosity in the coating, so it can adhere to it or create tissue ingrowth. But the main reasons why it actually loosens is because of fatigue of the hypoxyapatite, the fitting. So it might have been fitted during the surgical procedure, fitted wrongly, the surgical technique, and just overall long-term degradation and wear. So it's mostly reading up on those factors. And I've also included pages from the book where you can dive in detail if that's something you want to do. Any questions so far? Questions from last exam? All right.
I have a question about it, sorry.
Yeah, go for it.
Can you go
back to it?
Yeah. So those would be like, why would it get loosened, right?
Yes.
What did you say would be so it wouldn't get loosened, so it gets fixed? Use the polarizing it?
So there's different ways you can go about it, but it depends on what type of material the device is made out of. If it's a polymer, then what you can do is instead of making a polymer in the bulk, you can composite the polymer so that it's made of a stronger material. That's one way to reduce wear on the material and therefore reduce loosening. If it's made of ceramic, then you want to include pores in the ceramic coating so that the tissue adheres to it. And if it's made out of metal, then you can alloy it with a stronger variation so that it actually wears less and it has a better fatigue life. Those are different ways to go about it.
Thank you.
Okay. So for number three, it talks about surgical tapes and why it's beneficial. The reason why surgical tapes are used is because you want to apply it on the surface and prevent damage, point damage that would be caused by sutures, because you have to go into the tissue and staples. The cons that come with that is that it gives a poor cosmetic appearance. The biggest one is that it actually might misalign the wound. So you might have misaligned wound healing. And overall, it's actually poor adhesion compared to staples and sutures. It might lead to the creation of abscesses and pus pockets and the wound drainage. So the only scenarios where adhesives, where surgical tapes may actually be beneficial is when it involves different parts of skin graft and neural connective tissue, and you want to put those all together in a mesh on the surface. So this one was a multiple choice question. Which one's not associated with bone cement? And actually all of these are. Bone cement, also known as hydroxyapatite, absorbs shock, so it has good compressive load, is viscoelastic because bone itself in the dry state is viscoelastic. It osseointegrates, so it also relates to viscoelasticity. Osseointegration is a surgical technique used when they input a titanium rod in the lower limb and they distribute the load so that you can use with the bone a prosthetic, and it has good load distribution. Number five, it talks about percutaneous devices. and the general model that is used to show a percutaneous device. So there's different regions in the percutaneous device. This is the device right here, PD, and it has an A region, a B, and a C region, and a D and E region. And those are just different phases at which the percutaneous device interacts with the skin at the epidermis, dermis, and hypodermis level. Some key points that you should be aware of is that the percutaneous device needs to be fixated on the skin, and it needs to be implanted well so that it's structurally sound. It won't be pushed out from the skin. And one way to overcome this is to have it free floating. But despite this, and despite those different zones, there's also forces that are exposed to the percutaneous device, which include torsional, radial, and vertical stresses. And so those are important because the skin will always be pushing outward or in some direction.
Alejandro?
Look here.
Yeah.
By any chance, do you know what chapter this is on?
Most of it covers chapters 10 to 14.
Yeah, I was
specifically this is it's chapter 11. It's figure 11:11 and figure 11:12.
For number 6, it was a formula. So when we went over this, he actually talked about it very briefly, but for the test, we just had to follow this formula and it was okay. It talks about the strength of material after implantation. So they give you the conditions and you just plug it in. And these are the values that I got at the end of those calculations. So it would.
Is this like a plug and chug kind of one, or?
Yeah.
Okay.
Does it tell you like the specifics for A and B, like which one's which, or like you have to know like the A and B?
Yeah, he gives you have to find A and B, and with the number of days, and then you would get those values. For number 7, this one's similar to exam 1. They give you a polymer and the degree of polymerization, and they want you to find the molecular weight. So the steps are pretty simple. You calculate the weight of one unit, and then you just multiply it by the number of units they give you, the degree of polymerization. This is how you would do it, and this is the values that you can obtain.
Okay. And yeah, obviously we just have to remember, like we just have to remember the molecular weights of hydrogen and carbon oxygen. Yeah, pretty straightforward. Okay. Yeah,
you can round those as well. I don't think he's going to give you a periodic table, but he'll for sure give you at least the values of hydrogen, carbon, and oxygen.
Oh, really? Okay.
I hope so.
So number 8, it relates to detailed theories of bone healing and how it would be used to actually improve clinical outcomes. So the major point you should know is that there's a theory that goes behind it called Wolff's law.
Mm-hmm.
And Wolff's law talks about the equilibrium mechanics of the bone when it's being produced and destroyed. And it also relates to the piezoelectricity of the bone. The reason why we can stimulate bone to grow when it's provided a mechanical and electrical stress is because of its piezoelectric properties. And for that, we can use it on devices to stimulate growth. There's a particular note you should understand is that this growth usually does not occur for diameters less than 75 micrometers. So if you want pore ingrowth in bone, then you should have the pores greater than that value. So that will be useful for ceramics.
Pores greater than 75?
Yeah.
75 micrometers, okay.
So because of this Wolff's law, you would have stimulation of the regional cells, osteocytes, then that would produce a metabolic activity to increase cell differentiation in that area. And that's due to the bone's piezoelectric properties. People that talk about it, that I can read up on, is Yasuda and Fukada. And these are the pages that go into specific detail with regards to Wolff's law and Yasuda and Fukada. Any questions so far?
No.
Good?
Yeah, we're good.
So for number 9, he gave us a thermal diagram from a differential scanning device, and he wanted us to talk about the different zones, the TG and the TM. So for those, he might give you a slight variation. He might give you one with 2 TG peaks or 1 TM peak. And he gave us this one. And from this, we can determine that it probably has 1 amorphous phase and 1 crystalline phase. Although there could be situations where you have 2 amorphous phases, or 2 TGs and 1 crystalline phase. So that would depend on the type of diagram he gives you. And
I have a question.
Yeah.
I thought that in the DSC, like the peaks were like the other way around. Why are they like inverted? Why are they like downwards?
oh yeah, the crops. That's not the peaks, the drop. Yeah.
Okay. But
It's
like,
just like a different kind of graph, really. Like he's shown us both from, but
Okay.
like
okay, thank you.
So you can give those descriptions, and that should suffice for that one. For number 10, he said it was big for this one, and he goes a lot over in detail in class. At least for we had it, and the book. There's a lot you can read up on it. So some mechanical devices used, although these are just 4 out of the many listed in the book, are the ball and cage, tilting disc, the butterfly, and the tri-leaflet. The tri-leaflet is different because it's actually synthetic, so it's not totally artificial like the other 3, but it's worth mentioning. So ball and cage was actually the first one developed, and it's the most simple in design. It's just a ball and a cage. And it's made out of titanium or other alloys, cobalt chromium, and it's usually coated pyrolytic carbon to make it less, to have less friction on the surface of the blood or other polymers. Some setbacks with this is that it actually causes psychological damage to the user that might need treatment because of the clicking sound. So this thing actually clicks in your abdominal cavity and you can hear it. Also, it makes the heart work much more than it needs to be because of the ball, and the heart needs to work to push the blood through the ball. Also, there's no central flow of blood, so the blood needs to go around the ball, so making the heart work more. The good thing about it is it actually lasts a long time. If you live that long, 30 years, 20, 30 years, so that's a lot of time. Tilting disc was an improvement on that. So instead of having a ball and cage, you just have one disc that tilts on its axis. And the material-wise is usually made out of the same material, but the improvements with this design is that it has improved blood flow motion. The maximum blood flow that you'll get is at 60 degrees, although it's not as good as obviously a natural valve. Then you can take this one step further. Instead of having a tilting disc, you have a butterfly valve in which you have 2 different leaflets fold on a central axis in one direction. It has improved blood flow, but it has less wear resistance. And finally, the tri-leaflet valve made of synthetic silicone rubbers. It attempted to mimic natural valves, but actually failed miserably because of the poor fatigue resistance and poor fatigue life. Other problems include regurgitation, hemolysis, and incompetence. If you want to in the book, there's several more models that they mention that you can read up on. And overall, when you compare mechanical versus natural valves, the pros and cons are the following. Mechanical valves actually last longer. They have better wear resistance overall. And you need to maintain them in the sense that once you have it, you need to take treatment with pharmaceuticals to prevent clotting. So you would have heparin, warfarin, or novel oral anticoagulants, which are the NOACs. If you're taking a natural valve replacement, then you might want to consider bovine and porcine, although you need to treat those as well to prevent any sort of infection. And the way they treat it is usually with chromic salts, and they link it with glutaraldehyde groups. So that's one factor that mechanical valves don't need to do.
I thought heparin would be wouldn't be like a coagulation. It would be like a thinning.
So those are different. So for coagulation, there's different phases in it. Warfarin blocks one phase versus heparin, which blocks another phase. And both, oftentimes you take both to make sure that you don't start the cascade formation or you prevent the actual thrombus. Yeah.
Okay.
what are the he mentioned in class, I think that he said like the main valves that are used are the ball and cage and the bileaflet, right? Like the other ones, like they don't really use them anymore, right?
Yeah, for these, the ball and cage is the most common because it's the cheapest to produce, and then bileaflet valve because it has improved blood flow. But the other ones, they are harder to manufacture, and they probably have less synthetic they probably have less wear resistance compared to if you have a natural valve replacement. So if you get a porcine or bovine heart valve, then you might have better results than those than having a synthetic valve of a trileaflet valve, just because of the material selection. For number 11, we actually did not understand that question when we had the test, but this is what we had so far. So when you have a stainless steel rod and they wanted you to calculate the bending stress, the reason why it was left incomplete is because, at least so we think, is that you can't calculate the bending stress one if you don't have the length of the rod. So if you guys understand this question and can find the answer, then kudos to you. For number 12, it was 5 questions. So he wanted us to answer these 5 different questions. For number 1, it was the pros and cons of self-tapping versus non-self-tapping screws. As it says in the name, self-tapping actually make their own thread, and non-self-tapping don't. So for non-self-tapping, it would be different because you would need to, let's say, drill the hole and then pull it out and then put in the nail. And for self-tapping, it will make its own thread as it's being drilled, so you don't need to pull it out during a surgical procedure. And this holding strength is about the same. What's different about the holding strength is that as you increase the radial or the radius or the radial distance of the screw, it actually becomes harder to pull out. So rake angle is pretty straightforward. You have positive rake, negative rake, and zero rake. And for positive rake, the major differences between positive and negative rake is that positive rake, you need to apply more force when you're drilling it, but it actually, and it shears more, it shears less, but it will cut faster. So if you're drilling something and you have a positive rake angle, you need to apply more force to it, which is why you see probably, like at least my dad leans against the drill when he's drilling something, so that's probably a positive rake angle. And our negative rake angle is different. So instead of having more force, you can apply less force, and that's one pro for it. You apply less force, but the temperature you need to reach will be higher. So you'll be having more temperatures because of the amount of rotations you would be drilling it at compared to positive rake. And zero rake is just as it is, easy to design, manufacture, and easy to maintain. Degree of firmness of fixation, and how does it influence healing? So this one was pretty straightforward. You want it to heal in surgical devices. You want the surrounding tissue to heal. So when it involves screws and other types of devices, surgical devices, you want to let the tissue heal in the early phases of recovery, because your surrounding areas are going to necrose, but once that's done and you let the tissue heal, it should be fine. And in terms of fixation, you don't want it to be that firmly fixated because of this necrosis factor. If you firmly fixate it, you're going to cause local necrosis and local inflammation. So you want it to be more or less loose, but still adhesive to the local tissue. Number 4 goes over the pull-out strength of different designs of screws. And honestly, I believe it's in the book, they should be the same across all 3. What's different about the designs of the screws would be, I think, the radial. Again, the radial distance. The bigger the radial distance, the harder the pull-out strength. So the bigger the pull-out strength. And the last one would be, what would be a load environment explained by a plate and treating a fractured femur. So it talks about more or less stress shielding. And stress shielding basically says that, for example, when you go to surgery for someone who's getting a lower limb implant and they get a bone plate, then that bone plate will, in the sense, take the load that is applied to when you're walking. Now, since bone needs stimulation in the form of mechanical stress or compressive mechanical stress to be stimulated and regrow, stress shielding is bad for local growth because you want the bone to be strong. And because the plate is taking the load, the bone won't be able to stimulate itself to regrow. And so these are some practice problems you guys can read up on. And within the book, it relates to similar applications where you discuss pros and cons and where or where not would a theory be applied. So we have total hip replacement and a 3-component viscoelastic model of bone, which is the same as a standard linear model. And here are different models, and this is the one that you're looking for, the standard linear solid model. Spinal implants and knee hip joints, and hydroxyapatite, which is bone cement. Any questions, guys?
How would you derive that last one? I don't think you ever. Is it like a combination of the Maxwell and the Kelvin, or is that like just done like a different way?
So structurally, it is a combination. Mathematically, I don't know how to answer that question because
I don't think he said that we needed to know that. We needed to know how to derive both of them.
You're right. You do need to know how to derive it. I just don't know how. I would be the wrong person to ask, but I do believe, obviously, when you look at the Kelvin and the Kelvin in the Maxwell model, when you look at the diagrams, it's just a spring and a dampener in series. And for this one, it's just a spring and dampener in parallel. When you look at the SLS model, it is similar to the Maxwell with just the addition of just one more spring. So you're right, it does have combinations of both, but I wouldn't know the step-by-step of how to derive it. Either way, the final product should be this, what you have here. That would be the final product of the derivation. He's still going to pull questions from past exams, so what you don't see here covered, I would look at the other reviews or any other content that he may give you, that I may have given you before, and told you to remember, because he will probably still test you on it.
Alejandro, you put on the second in the second test. I don't know if you have it somewhere close. You put something about pathophysiology. What was it, Chris?
It was described two responses that are pathological and non-pathological, and then you put like a diagram from chapter 10, and it had like the chemically induced response, a physically induced response, and a necrotic response, and the minimal response of like a tissue encapsulation. Our question is that when you're giving two different responses for pathological and non-pathological, what would that be? Would it be two that are systemic and two that are cellular, or is it like just using that picture where you say that like two of them are coming from the chemically, like would pathological be like the chemically and physically induced responses of like inflammation, and would non-pathological be the necrosis and the minimal response of like tissue encapsulation?
I'd say that's about right. I'd say that's about right. Anything that's not normally leading to good tissue regrowth would be non-pathological, or would be pathophysiological, because you want it to actually have positive regrowth.
Okay, all right.
But it also depends on the material of the implant you're using. So obviously, a different physiological route would be for a metallic implant than it would say a polymer implant. So that just depends on the different types.
Okay.
All right. Anything else you guys want to cover? All good on your end?
Yeah, for sure. So you could never figure out the one that you said you never finished. You said you couldn't figure it out because you didn't have like the length of it.
Yes, for this one.
Okay.
So this is actually a really simple formula. You have the force applied versus the cross-sectional area.
Mm-hmm.
So you take the stress, and then we can't do anything with that because you don't have the length.
Okay. All right.
We don't have the length to calculate what the
steel rod.
The bending stress moment.
Oh, okay. Do you think we need to know he talked a little bit about the moment of inertia, but I don't know if we should go over that. It's a little bit.
So moment of inertia, that's his first exam, if I believe. He'll actually give you the formula for those. So all you need to remember, at least all we had to remember, was how to calculate it in case we did get the formula. And so which variables will be of course the ones used. The easiest one to go over is the rectangular one. So he's going to give you probably a I-beam or an L-beam, and it'll tell you to calculate the moment of inertia of that.
Okay, thank you.
Did he stress like the materials used for like hip joint replacements and knee joint replacements? Like, did he stress that at all when you were like?
So yeah, one question you might bring up is the different classes of materials used for those applications. So you want to have prepared one type of material class for each application. Okay. So in that case, a polymer for that could be polyethylene for knee joints, or a ceramic could be hydroxyapatite.
Okay. So like have like a metal ready, a ceramic ready, a polymer ready.
Yeah.
Okay.
And the reason why you apply it.
And the reason why you apply it. Okay. And then for like for the spine, you think he was like stressing like specifically rigid spacers. I don't know if he mentioned that to you when you were taking the class, but like it's just like when I read it, like it was kind of like all over the place with the materials that are used, and it didn't really give like a whole.
So regarding spine applications, we actually did not cover that for the last semester.
Okay.
But I did go over the book, and you're right, they do go very spread out in terms of what's used. I would say just classify the different categories. So you're gonna have the spacers, the interdisc spacers. You're gonna have the fixated ones,
Mm-hmm.
and
I guess you just have like a general idea of like the difference between the ones.
Yeah,
like the pros and cons.
So the spacers are gonna have obviously different uses than the fixated ones, and they're gonna be made of different materials as well. So you will have different considerations in terms of creep, in terms of viscoelasticity, in terms of mechanical stress.
Okay. And then he also asked us this, and like I was like kind of confused at the question. He's like for dental restorations, he's like what joints are involved, and the only thing I could really get at was like the teeth and like the surrounding bone. I don't know if like there's any like joints like that are involved in like like in there. I don't know if you know of any.
So the maxilla.
The maxilla.
Yeah.
Okay.
So that would be just your lower jaw.
Okay.
You could talk about the interface between the lower jaw and the upper jaw, or with your cranium.
Okay, lower jaw, upper jaw, and cranium.
I know the pages mentioned down here in one of these questions points to the book, and it actually goes over that. So which one? I think it's this one. After spinal implants for this one, they talk about dental implants as well.
Okay.
So just look on the PDF for those pages, and you'll find it.
Yeah. No, it's there. It's kind of it's the spinal ones and like the dental ones that are kind of like really spaced out and like have a lot of like random info, and it's not really like but I'll definitely look at it. I just don't know what kind of question you would ask.
So he might ask you the anatomy of it.
Okay.
The anatomy of a dental implant, in which you would have the actual screw, and then a sort of head over it, which would equalize the load distribution, and finally the crown.
Okay.
So he would ask probably stuff like that.
Okay. And Carlos should know all about it.
All right.
Nothing. All right. Thank you, Alejandro.
You're welcome.
I appreciate it, man.
Any other questions, guys?
Oh, one more. Maybe you know. He said he's gonna give us like a bonus question, and he was all like, it's something that we like use, like we've been using or talking about like every class. I think it's like biocompatibility. I feel like that's like the most like.
I think it's 10 to the 6th life cycles.
I have no idea. I wish I knew, but I can tell the bonus question he gave us. Sometimes he does repeat it. So, and on past exams you can see actually the bonus questions he gave them. So maybe he repeats it. One question he did give us. He drew us a 4x4 square. Okay, and he asked us how many squares in a 4x4 square.
There's infinite.
No, it's 36.
Why is it 36? Oh, that's why.
30. It's 4 factorial. It's 30, no?
Yeah, but you also count the squares inside the squares.
But if there's like whatever, what like? Okay, never mind. I'm not gonna get that deep into that.
So you guys can do the math, but I think it should be 36. He either give you a 3x3 or a 4x4, and it's probably the 4x4. And so he'll ask you how many squares inside that square. Something.
I won't do that one because he told us that we talk about it every day.
I don't know.
Maybe if we learn by having fun.
Maybe.
Oh, that's true. That's true. You just say that every day.
Having fun.
Yeah. No, that's good though. So like a 4x4 square have 36 squares. Do you know how many 3x3? How do you go about calculating that, Alejandro?
So for the
Well,
3x3.
I'm pretty sure it's 4 factorial. It's 30. Because usually when they did that in like calc, you just count how many original squares, and then you would just do the factorial of it. So like for 5, it would be let's see, 30, 55, I think.
So that was one question he asked us. The second one that actually appeared on a past exam was, what year did FIU win some football game or something like that, and against who? And that's just a history buff question. So I lost that right away.
Who would even know that? College,
I
you
don't know,
probably
man.
know
I
that.
would know that, dude. I love FIU football.
Oh, we won against UM last year, no?
Hell yeah, we did. We gave them the smoke.
So that pretty much sums up the questions that we had so far.
All right. Thank you, man. I appreciate it.
Thank you, Alejandro. All right. So obviously, if this is your first time doing this, then if you want to join the group chat, we'll have all the study guides there. Just scan the QR code to my top right or to your top left, and good luck tomorrow. We'll be having, we'll be planning on doing more of these for the fall, probably transport. So we'll see about that. But also, lots more coming in the fall.